Hi, my name is Zhang. I'm from the Department of Chemical Engineering and Material Science at the University of Minnesota. In this presentation, I'm going to talk about some recent work we've done on optimization under decision-dependent or endogenous uncertainty, and specifically within the context of robust optimization. So there are different types of endogenous uncertainty that have been considered separately in the literature. And our main contribution here is that we develop a unified approach that can capture multiple types within the same model. And that allows us to consider a number of interesting problems that we previously weren't really able to properly model. So this is joint work with Wei Feng from Zhejiang University, who was a visiting PhD student in our group. Endogenous uncertainty has its origins in stochastic programming. So here I'm just listing two seminal papers on this topic. And usually we refer to two types of endogenous uncertainty, type 1 and type 2. In type 1, decisions can alter the probability distribution of the uncertain parameters, whereas in type 2, decisions do not affect the distribution, but they do determine whether and when uncertainty is revealed. Now, we would like to refine a little bit the classification of type 2 endogenous uncertainty by defining what we call type 2A and type 2B. So in type 2A, decisions determine whether and when uncertain parameters materialize, which means that they actually become physically meaningful. Whereas in type 2B, decisions determine whether and when the true values of uncertain parameters are observed. Most existing works, they don't really make this distinction because they assume that if an uncertain parameter is materialized, it will also be observed, but that's not always true. So here are two examples where, depending on the problem, the endogenous uncertain parameters can be any of those three types. So the first example is one that we're all familiar with as chemical engineers. So that is the uncertainty in the quality of a chemical product, which typically refers to the chemical composition. So it can be a type 1 endogenous uncertain parameter if, for example, its distribution, probability distribution, can be affected by the process design, which may include the design of a chemical of a process control system. It is type 2A endogenous because it only materializes if we actually produce that product. And because chemical composition can be very difficult to measure online, it's often only observed once we take a sample and analyze it in the lab. So that makes it also type 2B endogenous. The second example is product demand, which for us is typically an exogenous uncertain parameter because we consider problems in manufacturing where our decisions usually can't affect the product demand. The situation changes though if we're in marketing, for example, or consider a revenue management problem. So then product demand can be type 1 endogenous if, for example, we can affect its distribution by changing the price. And also if it's a new product that hasn't been launched yet, then it's also type 2A endogenous because the product demand, the uncertainty in the product demand will only materialize after the product is on the market. And finally, the true value of the product demand is only observed when an order is placed. So if we can affect that timing, for example, through a contract with a customer, then it's also type 2B endogenous. So what does this all mean in the context of robust optimization? So let's take a look at this using this two-stage formulation here. So here, X are the first stage variables and X tilde are the second stage recourse variables, which is why they're expressed as functions of the uncertain parameters Xi. Without loss of generality, we'll assume that the objective function is deterministic and the constraints are such that they have to hold for all Xi in this uncertain set, capital Xi. With endogenous uncertainty, there are three major components of the problem that the first stage decisions may affect. So the first one is, of course, the uncertainty set, which is now decision dependent. We will talk about this in more detail on the next slide. The second is what we refer to as the deterministic feasible set, which is the set of feasible second stage variables for a given X and Xi. So this set should only depend on materialized parameters, since parameters that do not materialize and hence are not physically meaningful, they should be irrelevant for the problem. And then third are the recourse decisions, which can only be functions of observed parameters. because we need that information, those observations, to actually adjust these decisions. So here we cover these two components. Now let's see how the uncertainty set changes depending on the type of endogenous uncertainty. So say we have two uncertain parameters, CA and CB. If they're exogenous, the uncertainty set is fixed and it may look like this. If we have type 1 endogenous uncertainty, our decisions may change the shape and size of the uncertainty set. If we have type 2A endogenous uncertainty, our decisions could, for example, affect whether CA materializes or not. If it doesn't, we're left with only CB, and then the uncertainty set becomes the projection of this full space uncertainty set onto the space of CB. So then it's just this red line over here. In the case of type 2B, we decide whether to observe the true values of the uncertain parameters. So say that both uncertain parameters have materialized already, but if we don't observe their true values, they remain equally uncertain to us, and the uncertainty set doesn't really change. But if we observe CA, and which has a true value, say CA bar, then the uncertainty set for CB reduces to this line here. And if we also observe CB, then the uncertainty set reduces to this point, which essentially means that there's no more uncertainty. So the literature on robust optimization with endogenous uncertainty is rather scarce. So Paulson, Nohadami, and Sharma, they have addressed type 1 endogenous uncertainty. Aframidou and Pisakopoulos have outlined an approach to this problem using multi-parametric programming. Lapas and Gunaris have considered type 1 and type 2A, but most of these existing works, they only consider the static case, so with no recourse. And recently, we have extended this to the multi-stage case, where the uncertainty set can also be affected by recourse decisions. And what I'm presenting here is really kind of an extension of this work. If you're interested, Wei Feng is giving a talk on this in the session on design and operations under uncertainty. And finally, Vianos and co-workers have done some great work on type 2B endogenous uncertainty, and they really show very nicely what I'm about to talk about on my next slide, which is how this all relates to active learning. So active learning can be defined as the design of experiments with the goal of reducing uncertainty through observing the outcomes of these experiments. So the geometric interpretation in our set-based setting is that the observations correspond to cuts that are added to what we call a prior uncertainty set, which then leads to a reduced, smaller posterior uncertainty set. So here's an example of a problem where we want to build an industrial scale plant, but Q, which is the capacity of that industrial scale plant, once it's built, is uncertain. However, we can build a smaller pilot plant whose capacity is also uncertain at this point, but once we observe it, it will give us a better idea of what capacity to expect for that big industrial scale plant. So this is the uncertainty set involving both uncertain parameters, and we can see that they're clearly strongly correlated. And the prior uncertainty set for Q is this range between Q min and Q max. If we decide to build a pilot plant, then we will observe a P bar, and this P bar then will result in a posterior uncertainty set for Q, which is in this range, which is much smaller. And this information can help us decide whether we want to move forward with investing in this industrial scale plant. I won't go into much detail here, but it turns out that we can formulate this multi-stage robust optimization problem involving all three types of endogenous uncertainty as follows. So for simplicity, we assume fixed recourse. Here, Y is a binary variable that indicates whether an uncertain parameter materializes or not. Similarly, Z is a binary variable that indicates whether an uncertain parameter is observed or not. So then these equations here really state that our recourse decisions have to be functions of uncertain parameters that have been observed up to this point. The decision-dependent polyhedral uncertainty set can be formulated like this. And then we'll also want to note that these constraints here also include these ones, which state that an uncertain parameter can only materialize within certain times, it can only be observed within certain times, and uncertain parameter can only be observed if it's actually if it also materializes. And to solve this problem, we use nonlinear decision rules based on the concept of lifted uncertainty. So we use piecewise linear decision rules for continuous recourse variables and piecewise constant decision rules for binary recourse. And the main technical innovation here is the modeling of decision-dependent non-anticipativity, for which we introduce auxiliary uncertain parameters. So we end up with decision rules that are linear functions of lifted auxiliary uncertain parameters. And this also allows a duality-based reformulation. So then that leads to a model that can be solved using off-the-shelf solvers. For the rest of my talk, I'd like to go through 3 case studies that show what kinds of problems can be modeled using this approach. The first one is maintenance planning with inspections. So here we consider uncertainty in equipment degradation, which is often difficult to measure. In this case, we assume that the remaining useful life, or RUL, from equipment unit can only be observed through an inspection. So this problem actually involves all 3 types of endogenous uncertainty. So we consider the option of equipment upgrade, which would reduce the range of possible values for the degradation rate. So that's type 1. Degradation only occurs when we actually operate in that unit. So that's type 2B or 2A. And we need to perform an inspection to observe the RUL, which makes it type 2B. We consider 2 cases. So one with a high cost of upgrade, equipment upgrade, the other one with a low cost. And for each, we solve the problem with a static RO model and then with adjustable RO model. So this really shows the value of recourse. So you can see that the optimal value improves when we have recourse, but it also comes at a computational cost. And then just to give some physical insight here, if we compare these 2 cases, we see that in case 1, no equipment upgrade is selected. And so inspection has to occur relatively early. And then depending on the result of inspection, we either have to perform maintenance right away, or we can wait until a later point. In the second case, we do invest in equipment upgrade, and that allows us to perform inspection at a later point. Next, we consider the problem of optimizing revision points in capacity planning. Recently, Bashevta et al. Have introduced this notion of adaptive 2-stage stochastic programming in the context of capacity expansion. So the idea here is that capacity decisions are bound to long-term commitments, so they can't be easily updated every time new information arrives. So rather, we want to determine a small number of what we call revision points, and these are times when these decisions can be updated. So if we think about this in terms of a scenario tree, then this one will correspond to the case when there's no revision point. Here, the revision point is placed at the second time point, and here it is at the third time point. So we can see that the selection of the revision point really defines the decision stages of our problem. And it turns out that this can be modeled as a problem with endogenous uncertainty, or more specifically, as type 2B endogenous uncertainty, where the time of observation of uncertain parameters is essentially the revision point. In fact, here we can actually consider more than just one revision point, and we apply this to a simplified power generation capacity expansion problem with 7 time periods. So here we see we solve the problem for different numbers of allowed revision points. Here we see that the optimal value improves with the number of revision points, but we also see some diminishing returns at some point, where in fact, for some of the technologies, we don't even need as many revision points. Finally, in our third case study, we'll consider process scheduling with active parameter estimation. So the setup here is that we have a new process that can operate in different operating modes, but we haven't operated in them yet. And we assume that each production in each mode, the production amount is a function, in this case, a fine function of the input variables u. So these model parameters A and B, they are uncertain, but we can estimate or learn them by operating in that mode, so from operational data. So for example, if u is an n-dimensional vector, then we only have to operate at n+1 different operating points to estimate A and B. But to do so, we have to operate in that mode. So this is really a classical problem of balancing exploration and exploitation. So here we just consider a small illustrative example with 2 operating modes and 2 discrete operating points per mode. There's only 1 input for each mode, so only 2 unknown parameters in each model. The solution here tells us that to first operate at the first operating point of mode 2. Then if the resulting production amount is greater than a certain value, we will later operate in that mode again. Otherwise, we just keep operating in mode 1. So considering this uppercase here, this is how these parameters are optimized, are estimated over time. So in time period 1, we operate at the first operating point of mode 2. So the associated production amount could be anywhere on this black line here. Now let's say it turns out to be this light blue point here. Then immediately the uncertainty set for the second operating point reduces to this little bit here. The same thing happens when we operate at the first operating point of mode 1 in the second time period. In the third time period, we also operate at the second operating point of mode 1, and then both of these observations will give us the exact model for mode 1, which is represented by this red line here. And then finally, in time period 4, we also operate at the second operating point of mode 2, which then gives us the model for mode 2. So this, of course, is a very simple case. We can extend this to more complex systems, but right now computation is still a challenge. Now, finally, let me just conclude with some key takeaways. The main one, the one that I really want to get across is that there are a number of interesting problems that require optimization with endogenous uncertainty. And I hope I was able to show this with examples and case studies in this presentation. There's a strong connection between endogenous uncertainty and active learning, and that's something that hasn't been explored as much in the context of robust optimization. Our contribution here is that we propose an approach that can jointly consider multiple types of endogenous uncertainty in the multi-stage setting, also with both continuous and binary recourse. But there's much more room for further research, especially related to computational aspects. With that, I'd like to thank you for listening. Here's a reference to our paper, and I'd be happy to take any questions during the Q&A session or via email. Thank you.